Okay, good morning. Um, so today we're gonna start a new topic. It's a continuation of what we started discussing in terms of solving problems using the simplex algorithm. And in our first few lectures on the simplex method, we solved problems that only had constraints that were less than or equal to. And I explained that that's a special type of problem, but that not all problems will be formulated in that way. So the question now is, what do you do when you have a problem that the constraints are not all less than or equal to? How do you find an initial solution so you can implement the simplex method? And the answer to that question is we need to use what is called an artificial starting solution. Okay, so we're going back to solving these problems by hand, understanding how the simplex method works. And if you remember in our first lecture for the simplex, we were using the slack variables to provide that initial solution that was allowing us to implement the simplex method. But today, again, we are going to be looking at a different type of problem, and we're going to see how this artificial starting solution is going to help us to find that initial solution so we can implement the simplex method, or we can use the simplex method to solve the problems. Okay, so I had a question or a comment at the beginning of the lecture in terms of going over or at least have some time to discuss the lab that is due tonight. So we're going to do that towards the end of the lecture. So if you have questions about Excel and how to use Excel or AMPL, we can address those towards the end of the lecture. Okay, so the learning objectives for today is to use the simplex algorithm to solve linear programming models involving constraints that are equal to and constraints that have a greater or equal to sign. Okay, so if you remember, again, I'm repeating this over and over again, when we started implementing or solving problems with the simplex method, we were only focusing on problems that had less than or equal constraints. Now we're going to see what to do when we have constraints that are equal to or greater or equal to. So the agenda is to discuss what is called an artificial starting solution. And then we have two strategies to use that artificial solution to find an initial solution for our problem. Those two strategies are the M method and the two-phase method. So today we're going to focus on the M method. We're going to have an exercise that you're going to try to practice how to solve a problem using the M method. In our next lecture, we're going to study the two-phase method, and we're going to spend some time also going through a practice problem for that. So let's talk about the artificial starting solution. So this is a summary of what we've been doing for the first few weeks. Solving two variable LPs. We also know how to implement the simplex method. However, LPs or linear programming models in which all the constraints are less than or equal to with non-negative right-hand size were our main focus, and they offer a convenient all-slack starting basic feasible solution. So our initial solution was always given by those slack decision variables, those X. However, models involving equality or greater or equal to constraints do not provide that. They don't provide an initial solution because they don't have slack variables. So what we want to know is, okay, if you don't have that convenient initial solution, how do we find an initial solution for these problems? So the procedures for starting linear programming models with equality and greater or equal to constraints is to use artificial variables that play the role of lags or the slacks at the first iteration. The artificial variables are then disposed of at a later iteration. So we're basically using them just to find that initial solution, and then we're gonna discard them at some point. The two closely related methods that are introduced in this lecture are the M method and the two-phase method. So these are two ways of generating artificial variables and using those to generate an initial solution for your problem. So again, we're going to focus today on the M method. And the M method starts with the, the M method starts with the LP in equation form. If equation I does not have a slack, an artificial variable Ri is added to form a starting solution, similar to the all slack basic solution. The artificial variables are not part of the original problem. This is a modeling trick which is needed to force them to zero by the time of the optimal iteration is reached. So the idea is we're going to generate this, we're going to add these artificial variables, but we're going to force them to be equal to zero so they don't impact the solution of the problem. We just need them for finding that initial solution, and then we're going to force them to be equal to zero. So our solution is not going to be affected by those artificial variables. And they're basically discarded when we make them equal to zero. The desired goal is achieved by penalizing these variables in the objective function using the following rule. So penalty rule for artificial variables: given m a sufficiently large positive value, mathematically m will go towards infinity. The objective coefficient of an artificial variable represents an appropriate penalty if the artificial variable objective coefficient is minus m in a maximization problem or positive m in a maximization problem. I'm sorry, minimization problem. So the idea is we're gonna create this coefficient, this m coefficient, and this is gonna be a very big number. And it's going to be adapted according to the coefficients of your problem. So for example, if you have a model that is like this one, 2x1 minus x2, we are going to use an m value that is high enough that when you compare to these two coefficients, you know that that's going to have a major impact on the solution of your problem. So for example, if we make m equals to 1000, you know that the objective function is going to have that minus 1000 is going to have a high value compared to these two. And since you're trying to penalize your objective function, that minus 1000 in a maximization problem is going to force R to be closer to zero or be a very small number. So let me, I don't know why this is showing. Let me fix something really quick. Oh. I apologize. Those notes shouldn't be there. I think those are going to create more confusion. I'll fix this slides quickly. Okay, so again, we want to generate these artificial variables and we want to penalize them in the objective function. Penalize them in the objective function is going to force them to be zero by the time we reach the optimal solution. So if you have a maximization problem, you have a maximization problem, let's say 2x1 plus 5x2. In a maximization problem, you want x1 and x2 to be as big as possible, right? Because you want to create an objective function that is going to be big. You are maximizing. So you want x1 and x2 to be as high as possible based on the constraints. If you are minimizing, is the opposite. You want x1 and x2 to be as small as possible within the constraints. So let's say we are working with a maximization problem, and we have a problem that has constraints that are equalities or greater or equal to. So we need an artificial variable to help us find an initial solution. But the way we're going to do that is, okay, I'm going to need those artificial variables to find that initial solution, but I don't want to have a solution in terms of those artificial variables. What I mean is, I need them to give me what I need at the beginning, and then at the end, I want them to be zero. How do you make sure that they are zero by the time you solve the problem? You penalize them in the objective function. How do you penalize them in the objective function? Like if you're maximizing, you use a negative sign times the coefficient, and let's call that artificial variable R1. So R1 is the artificial variable. Okay, and that M is a coefficient that is going to be a big number. Let's say this could be a coefficient equal to 1,000. So what's going to happen? Again, R1 is a variable. So now we are saying M is 1,000. So in this problem, since you're maximizing, that negative 1,000 is going to force R1 to be zero and the optimal solution. Why is that? Because if you increase R1, your objective function is going to decrease very quickly. And that's what we want. We want the artificial variable just to be there for finding an initial solution. And then after that, when we solve the problem, those variables will have a value of zero because they are penalized very heavily in the objective function. So that's what this statement and this penalty rule for artificial variables is trying to explain. If we have a maximization problem, we want to use minus M because that's the penalty. And a very high penalty basically is going to force that artificial variable to be zero at the end of the problem. If you are minimizing, it's the opposite. We're going to make this positive. Why is that? Because as you increase R1, and let's say this is 1,000, as you increase R1, this objective function is going to become very big. And you don't want that. You want that to be small. So at the end of the solution, that variable, the artificial variable, should be equal to zero. You're going to see that with a problem, but this is the main idea of the method. The main idea is you are using these artificial dummy variables to find an initial solution, but since you are penalizing them in the objective function, by the end of the solution or by the end of you reach the optimal solution, they are going to be equal to 0. Okay, so let's look at this example. Okay, and here we have a minimization of 4x1 plus x2, and then we have 3 constraints. One of them is inequality, one of them is greater or equal to, and then the last one is a less than or equal to constraint. So the first thing we're going to do is we're going to set up this problem into standard form, meaning that we're going to set up this with constraints that are all equalities. So if you see that using E1 as a surplus in the second constraint and S1 as a slack in the third constraint, the equation form of the problem is given here. So you see, you don't have to do 3x1 plus x2 is already in the standard form. It's an equality. To make this one an equality, you need to subtract an excess variable. And to make this one an equality, you have to add a slack variable. So that's the standard form. Any questions about this? Remember how to set up this into equation form or standard form. We need that to set up the table for the simplex method. So at this point, this is something that we already know. Okay, so this is done. Now let's set up this table. Okay, so now we want to implement the simplex method. We have the equation form. So if you remember, for the objective function, we have to move everything to the left, right? So this is going to be z minus 4x1 minus x2 equals 0. So what that represents here is that we're going to have minus 4, you're going to have minus 1, then 0, 0, 0. And the coefficients of the constraints are the following: 3, 1, 0, 0, 3, 4, 3, minus 1, 0, 6, and 1, 2, 0, 1, 4. So the first question I'm asking here is, how many basic variables do we have in this setup? So remember, those basic variables are going to be, if you want to identify them from the Tableau, you can identify them by looking at trying to identify the identity matrix. So finding columns that are going to belong to the identity matrix will tell you that that particular decision variable is a basic variable. So if you look at these 4 columns, 5 columns, but the only ones that belong to the variables are these 4. The only one that has a format similar to the identity matrix is this one. The rest of them, they don't represent, or they are not set up in that way. So at this point, the only decision variable that is a basic variable based on the initial Tableau is going to be S1. How many do we need? Well, we have 3 equations or constraints, so we're going to need m equals 3. Can you easily obtain the basic variables needed from this Tableau? The answer is no, because we only have one that is in that format. If you remember, for the problems that were less than or equal to, we found that identity matrix really quick. But that's not the case for this problem. We only have one basic variable. Does it work to multiply row 3, this one, by -1 to make x3 a basic? Yes, no. No, it doesn't work. Multiplying the third row by -1 problem turns the problem infeasible, because this right-hand side will become negative. So, so we only have one. basic variable, we need 3. And that's what this new method for generating artificial variables is gonna help us, or she, get those basic variables that we need to find an initial solution. Yes. So we have 3 constraints, and we need a basic variable for each one of those constraints. So right now, we're talking about these 3 constraints right here. We only have 1. So adding artificial variables, when an initial basic feasible solution does not exist, an artificial variable Ri greater or equal to 0 can be added to the constraints. It guarantees a starting basic solution. Artificial variables are added only to the constraints with equalities or greater or equal to signs. Why is that? Because you don't need one for the ones that have a slack. You know, for a constraint that is less than or equal to, we can add a slack, and that will help us find a basic variable. For the other ones, you have to add the artificials. So they're only added to equalities or greater or equal to constraints. So the third equation has its slack variable, S1, but the first and second equations do not. Thus, we add the artificial variables R1 and R2 in the first 2 equations and penalize them in the objective function with MR1 plus MR2 because we are minimizing. So the resulting linear program is given here. We're going to have the minimization of z equals 4x1 plus x2 plus m times R1 plus m times R2. Subject to, so now you're adding an artificial variable R1 to constraint 1, and you're also adding an artificial variable to the second constraint. So look at, for the second constraint, you can observe that we already have an excess variable. We keep that, and we are adding an artificial variable to it. So the excess variable will still be there. And for the last constraint, or the third constraint, we don't need to add an artificial variable because we have the slack. So this is going to be the new formulation. And the starting basic solution now will be given in terms of R1, R2, and S1, which values are going to be equal to 3, 6, and 4. So let's look at the, so from a computational standpoint, solving the problem on the computer requires replacing M with a sufficiently large numeric value. So right now we're just saying M here, but we need to assign a value to M. M has to be a sufficiently large number when you compare against the coefficients in the objective function. So for example, here we have 4 and 1, so M could be 100. 100 will be sufficiently large when compared to 4 and 1. But if in this case, this was like 400 and this was 100, then M has to be 10,000 or 150,000, something that when you observe the difference is big enough, so your penalization is going to work. So sufficiently large numeric value. What value of M should we use? The answer depends on the data of the original linear programming. The penalty must be sufficiently large relative to the original objective coefficients to force the artificial variables to 0 in the optimal solution. In the present example, the objective coefficients of x1 and x2 are 4 and 1. And it appears reasonable to set M equals to 100 because M equals, 100 is sufficiently large when compared to 4 and 1. But if you use 1,000, if you use 10,000, it's going to be the same solution. It's not going to be different. What I'm trying to say is you don't want to go to 10,000 because when you're doing the computations, then you're going to be dealing with very big numbers. So 100 is reasonably high enough to be a penalization for this problem. So we end up with this. Again, this is the formulation, starting basic solution. So let's set up the Tableau now. We're almost there. And all we are trying to do here is to find an initial solution. So we can apply the simplex method. So we can look at the tableau. Again, this is going to be -4, -1. We set M to be 100. So E is going to be 0. And then this is going to be -100, -100. S1 is going to be 0, and this is going to be 0. And now our basic variables are going to be R1, R2, and S1. So for the first constraint, we have 3, 1, 0, 1, 0, 0, 3. We have 4, 3, -1, 0, 1, 0, 6. Here we have 1, 2, 0, 0, 0, 1, and 4. So this is the setup based on this information. But the question is this still resembling or is this format showing you the identity matrix that we need? The answer is no. Why is that? Because we have another step to complete since this is not 0. Almost there. Why is not 0? Because you have these coefficients for M. And if you look at the tableau is not consistent. Why is that? Because the tableau is saying R1 is equal to 3, R2 is equal to 6, right? This is the solution that the tableau is showing. This is telling you R1 is equal to 3, R2 is equal to 6, and S1 is equal to 4. But when you substitute these values in here, the tableau is saying that this is going to be equal to 0, which is not true, because if you multiply 3 times 100, that's 300. If you multiply R2 by 6, that's 600. So the objective function should be equal to 900, not 0, which is what's showing here. So we need to make sure that this tableau is consistent with the solution that you should have based on those values. So we just need to do one extra operation, and that will be solved. So before proceeding with the simplex method, computations for the zero must be made, consistent with the rest of the tableau. The right-hand side of the zero in the tableau currently shows that z is equal to 0. That is this value right here. The objective function is equal to 0. However, given the non-basic solution x1 equals x2 equals x3 equals 0, the current basic solution where R1 is equal to 3 and R2 is equal to 6 and S1 is equal to 4 will yield a 900 objective function. To eliminate the inconsistency, we need to substitute our R1 and R2 into 0 using the following row operation. So basically what we are saying is we're going to apply the Gauss-Jordan method and we're going to make this equal to 0 and this equal to 0 to make sure that this is consistent. And that's the operation that is, or the equation, this equation is showing that operation, how to make this equal to 0. So essentially, this is the tableau that we have right now. What we want to do is to make this equal to 0. So we are going to apply the Gauss-Jordan method. here, we're gonna multiply this times 100, and we're gonna add that to row 0. And then we are, so here, and then we're gonna multiply this row times 100, and we're gonna add that to row 0. So after performing those operations, this is how the coefficients are going to change. So 100 times this row is going to be 300 minus 4 is 296. 100 minus 100 plus minus 1 is minus 99. This is going to be 0. This is going to be 0. This is going to be minus 100. This is going to be 0. And this is going to be 300. So that's the first operation. The second operation is doing the same thing with this row. So this is going to be 100 times 4. This is 400 plus 296. So this is going to be 696. 100 times 300 times 3 is 300 plus 99. This should be positive 99. This is going to be 399. 100 times minus 1 plus 0 is minus 100. 100 times 0, this is 0. 100 times 1, this is going to be 0. 100, this is 0. And 100 times 6 is 600. So at the end, this is going to be 900. So that's the row that we have right here. Yes, so that one, we don't need to do anything because that has a value of 0 already. So we don't have to fix that one. We only do it for the artificial variables because they have a value that is different than 0. Yes. It might work, but I would like to go a little bit higher just to make sure that the penalty is high enough so we force them to be 0 at the end. 10 is, I mean, the difference is about 6. I will recommend you to go a little higher. Yeah, so make it clear that is high enough, it's big enough. Maybe going, if you're in the units, go to the hundreds. If you're in the 100, go to the 1,000. Yeah. Okay, so at this point, we are basically done with the artificial method. What we're gonna do now is to solve the problem using the simplex method. So everything we did was to reach this point. Now we have an initial solution. You can see that we have that identity matrix here, which is telling us you have an initial solution for this problem. You are minimizing. So the question is this a optimal solution? You have to look at row 0 in order to answer that question. So when we discuss this method, the simplex method and the minimization, we're going to look for the largest positive coefficient. So in this case, we have 2. So the result is that R1 and R2 are now substitute out, have a 0 coefficient in row 0 with Z equals 900 as desired. The last tableau is ready for the application of the simplex optimality and the feasibility conditions. The variable x1 having the most positive coefficient in the Z row enters the solution. So this is going to enter. So now we need to perform the minimum ratio test to specify who's going to lead. All right, so I know x1 is entering. So I'm gonna do the minimum ratio test. 3 divided by 3 is 1. 6 divided by 4. What is that? 3/2. And we have 4 divided by 1. This is 4. So the minimum is 1. So what that means is that artificial variable is going to leave. So we're going to substitute x1 by r1. So r1 is the living variable. Once the entering and the living variables have been determined, the new tableau can be computed by using the familiar Gauss-Jordan operation. So after performing the Gauss-Jordan operation, this is the new tableau. Okay, so I'm not showing those steps because at this point you should be familiar how to perform those operations. So basically what you're doing is you want to make this a R1 is leaving, so this column now, since x1 is leaving, has to look like this one. And we're gonna perform the minimum rate, the Gauss-Jordan operations, and that's the result. The tableau shows that at this point, we are not done. We still have a positive coefficient in row 0, which is x2. So x2 is gonna enter, and then we're gonna perform the minimum ratio test one more time. So it's gonna be 1 divided by 1/3, and this is 3. It's gonna be 2 divided by 5/3. So this is 6/5, and it's gonna be 3 divided by 5/3. And this is gonna be 9/5. So the minimum, is R2. So R2 is gonna leave. X2 is gonna enter, R2 is gonna leave. So continuing with the simplest computation, 2 more iterations are needed to reach the optimum. X1 equals 2/5, X2 equals 9/5, and Z equals 17/5. And that's the solution. That's the solution for the problem. Okay, so at this point, we're basically applying what we know. And you will see that by the end of the solution, R1 and R2 are not going to be part of the solution. Since at this point, we are already taking R2 out of the solution based on the row 0 and the minimum ratio test. Okay, questions? I think the best way to learn this type of thing is to practice. So I'm going to pass so for those of you who are in online, you have a lab. I'm gonna pass that same lab to the students here in class so we can start working on the solution. So here's the So we're gonna use the big M method to solve this problem. And we are gonna basically perform the same steps. First, you have to set up the problem into the standard form and identify if you have to add any artificial variable like we did here. Since in this problem you're maximizing, now your M times R will be negative. So if you add an artificial variable to your problem, that has to be with a coefficient that is negative. In your problem, you have a greater or equal to constraint and less than or equal constraint and a equality. So you're gonna need two artificial variables, and those are gonna be penalized with a negative sign in the objective function. So let me see if I can get you. Let me see. I mean, I'm gonna give you a couple of minutes and then I'll give you some extra guidelines. Because in that problem, you have a maximization problem. So in order to penalize that R in the objective function, you have to make it negative.
Yeah. Do we change the sign
In the constraint, no, those are positive. They're always added positive in the constraint. Good question. Yeah. Actually, R is always positive. The negative value is for M. So the coefficient is going to be positive or negative, but R is always positive. So let me give you some so if you set up your problem correctly, it should look like this in terms of setting the constraints and the excess variables, slack variables, or artificial variables. So you're maximizing 2x1 plus x2 minus mr1 minus mr2. For the first constraint, you have a minus e1 plus r1. For the second constraint, you have the slack variable. And for the third constraint, you have only an artificial variable. The name should be different. So if you have two artificial variables, you should name them differently. I'm using R1 and R2. Doesn't matter the number. If you want to call them R100, R2, as long as they're different names, then you're fine. Questions? So I'm letting M equal to 100. Again, the size of the coefficients in the objective function are units. So I can use 100 And then to set up my initial tableau,
Do you know that 100 multiplied 3 over M?
that so basically what I'm saying is that, I mean, it's what I did for the example. I'm just illustrating that initial tableau is not consistent with the solution. So basically what this is saying that R1 equals 3 in the initial tableau and R2 equals 3. But the objective function is saying that this is equal to 0. But when you put that 3 in the objective function, you see that that is not true. You have a 0 here, you have a 0 here, you have 3 times 100, 3 times 100. So that objective function value should be 600, negative 600. And this is it. So that's why we need to make sure that we make this equal to 0 and this equal to 0 in the next iteration. Yes, it's negative, but remember when you move them to the left, they become positive. It's like 3, when you move them to the left, yes, you are making them, you're changing signs. So 3 change signs, 1 change sign, M change sign, and all of them change the sign because you're basically setting up your objection function. Yeah, I moved them over first. Y minus B minus 2x x2 plus M R1 plus M R2 equals 0. And those are the quotations that are going to go into the rows. So in my first table, I'm showing the result after making this. So R1 row 0 for R1 needs to be 0. So I'm multiplying row 1 by minus 100. And then adding that to row 0. And that's how I got the minus 103 minus 101, the 100 for E1, the 0 for R1, the 100 for R2, the 0 for S1, and the minus 300 for the right-hand side. And now, after this one, I need to do the same thing for R2. I need to make this 100 equals to 0.
So for this case, I think so. I followed the example we did and first make the table without cars, and we can say our basic product basic variable will be just 1 as well 1.
And you need 3. So then you are creating that here. This is the initial tableau because you're adding R1 and R2 to find that initial solution. So that's correct. And now you're trying to make this equal to 0. There's a result from here, and then you will try to make this one. Yeah.
So semantics. And what the second order basically typically you want to get a large number. The rule can come under the
So this is in maximization problem.
the largest negative, but I'd have to pick one. The largest negative will be this. Yeah, so it's
So for maximization, we pick the largest negative coefficient, and for minimization, we pick the largest positive coefficient. So in this one, so here's for the minimization, we pick the largest positive coefficient. In the lab, we're maximizing, so we pick the largest negative coefficient. So in that case, like after performing the second, you should have something like this. And then the largest negative coefficient is X1. And then you perform the minimum ratio test. And the minimum will be 2, so S1 will be leaving the solution. So at this point, you're basically applying the simplex method. You have completed the process of finding an initial solution. So from this point on, you are solving the problem using the simplex. So tonight you have to submit this lab and also the lab for the computer solution. So don't forget about that. And so I think I'll let you work until 10:30, and then we're gonna talk about the Excel stuff for a few minutes. Let me start opening that file. So if you have questions about the Excel assignment, now we're gonna talk about that. If you are okay, you don't need to, I mean, you can continue working with your stuff. But I guess if you have questions now, you can ask them. So this is the one that you have, that we did for lab 5. So this is the setup and the solution for lab 5 for the single period production. And now you have to implement that one in Ample. So you know the solution. I met with a couple of students yesterday during my office hours, and they were successful doing the Ample code. So was happy to see that. Few things to remember when doing Ample. You had to specify the greater or equal to constraint for the decision variables. If you don't have the constraint for the decision variable, let's say x1. If you don't let Ample know that x1 has to be greater or equal to 0, you will get an unbound solution. So you have to specify for your decision variables that they're going to be greater or equal to 0. You have a question? Yes.
Just now, but
Yes.
I have zeros with my changing the.
You got
Should I change values before I let's say
well, if you so decision variable, you can value more. Select the cell for the decision variable. That's how to let you go.
and this is
But I think that's the problem. That is only- Yeah, but that has to be allocated. So that can say x1 plus x1 equals 100. So that's what you need to calculate. You have to make that is the
then equal plus this. Oh no.
x1 plus x1 equal 1. Then so you have to set up a formula equal.
Versus with this equal this plus this.
Yes. The next one, we'll do that, you solve it again.
You have the same number, so I'm gonna make it good. Pick one.
Yeah, both of them are artificial variables.
Mhm.
Yes, so pick one. My advice is if they were not both artificial variables, you always pick the artificial variable because you want to get rid of the artificial variable as soon as possible.
Yeah, because it's not like 800 should equal 800. So that should-
Yeah, this side is always a formula. Okay, so if you don't have a formula there, then something is wrong. But this side is always a formula. A formula that uses the decision variables. Same thing with the objective function. The objective function is always a formula that uses the decision variables. Let's see how far we are into this. So it looks like you're right. You have the same ratio for both artificial variables. So you pick one. No, since both of them are artificial variables, you can select either one. But what my comment about if you get, for example, this minimum ratio test is the same, and you have to decide between an artificial variable and a non-artificial variable, then you always select the artificial variable because you want to take the artificial variable out of here as soon as possible. Okay? But in this case, both of them are artificial, so you select one of the two. But if you have to select between these two, for example, you select R2 because you want to take R2 out of the solution. Not necessarily. If at the end in the solution, you still have an artificial variable here, you have to make sure that the right-hand side is equal to 0. That's the only way that you can keep an artificial variable here. If it is not equal to 0, then the problem has no solution. And we're going to talk about that in our next lecture. X2 is the highest negative, so that one is entering at this point. Yes. And then you select which one is going to leave based on the minimum ratio test. So if you go to the next tableau, you see this is the optimal solution. And this is what I was saying. In the optimal solution, you see that R1 is still there, but R1 has a value of 0. So it's not impacting your solution. If it's still a basic variable and it's equal to 0, then you're good. Because that's what the non-basic variables are variables that are equal to 0. But if it's still a basic variable here and it's equal to 0, then you're fine. If that R at the end is different than 0, then the problem has no solution, because there's no way that you can find a solution for the problem without the need of an artificial variable. And we're going to go back, we're going to talk about that in our next lecture. I'm presenting you with the solution, okay? But make sure that you try to go through this on your own, so you make sure that you're understanding what's going on. I know, if you want to get the full credit, that's fine, but the important thing is that you go through the experience, because in the exam, you will have to do it by yourself. I think I can show both of the tableaus here. So these are the two final. And then if you are at home, make sure that you submit by tonight. If you are here and you have your solution in the paper, just take a picture and upload it to Canvas. Sure. Yes, yes.
Like, I get.
Oh, 'cause you entered R1 instead of R2, right? Should be getting the same solution anyways. So this is the same tableau, right? Yeah. 99.5, 1/2, -1, yeah. Yeah, it's the same thing.
Because to get rid of this, I need to multiply this row by 99.5 and then add it to this one.
Yeah.
But when I do that, I get negative 199, and then I add that to 100, and I get negative 99 here. Yeah, 100.
Let's see. Okay. So you're trying to get rid of the 99.9 on negative 99.5. You're multiplying. See. So first you multiply by 2, right? You make that a 1. Okay. And
Which meant that E1 was like a negative 2.
-2, you're right. So now you're trying to get rid of the 99.5. So this is -2. And you are multiplying by 99. So that's 199 negative. And then you are, and that's negative 99. Right. So your solution is going to be different because I'm dealing with R2 instead of R1. You see what I'm saying? Yeah.
So mine wasn't wrong.
No. Yeah. So you choose a different artificial value. through here. No, you can scan it and upload it. So the GIA will take care of the grading. Okay, we have a couple of minutes. Any questions? Okay, so if there's no questions, then I'll stop here. And we'll talk more on Monday.